Hi, I'm Ashay. I'm an engineer by training and a storyteller by passion. I made this podcast to talk about data science, but no math, no equations, just intuitions behind data science. The episodes are not in any particular order, and you can just tune into any episode and listen to something related to data science. Let's get started. When we have data, and when we do data analysis, uh, there are a couple of things that we can do with data analysis, right? So one is the data is always going to reside in a sample space within an infinite population, and then what you could do is you could only understand the behavior of the data within the sample space, or you could create an equation for how the data is related to each other, how the features of the data are related to each other, and then you can use that equation to understand the behavior of the data in some other sample space within the same population, which is not what the other sample space that you are not working with, but you could still understand the data in that sample space. So for that particular purpose, for understanding the behavior of data in some other sample space that you are not working with, and to create a prediction equation or a correlation equation for the features of the data within the sample space that you are working with, you need to have a generalized equation. And by that, what I mean is, you can't create an equation for the behavior of the data. You can't create a recipe of the data that only works within the sample space that you are working in. You need to have a generalized model which can be transported to other sample spaces too, and then you could be understand the behavior of data in those sample spaces. So how do you generalize this? So let's talk about two extreme examples. So um, if you create an equation, if you basically create, let's say, a line that passes through every single point of your data in the sample space that you're working in, and then you create an equation of that line, that's basically what you are doing is you are introducing tremendous variance in your sample statistics and in your estimation of your population parameters. So it is kind of like saying, if you want the equation for your sample space, if you want that to predict every single data point in your sample space the exact same way, as it appears in the sample space. So it is kind of like saying that there is a group of people, and the age range for that group of people is between 1 and 100. This particular piece of information is useless because you don't get much information about it. Obviously it is going to be between 1 and 100, right? But if you create an equation that tells you that the age range for a particular group is between 20 and 30, and then there are some outliers which are like maybe 15 or maybe 60 years old, then this gives much more concrete piece of information, because it tells you the generalized a statistic, a generalized estimation of your population parameter. And that's exactly what you want. You want to reduce the variance of your prediction equation or of your estimation of a population. But that's one extreme case. The another extreme case is if you reduce the variance so much that you are only looking at only certain points within your sample space and you are not actually capturing all of the information. Like for example, again in the group of people example, if I say, okay, the age range for this is only 20 to 22, but then that is only talking about maybe only few people within that sample space, and not it is not a generalized equation. So what you just did by reducing the variance to this extent is we introduced a heavy bias in the information about the sample space and the information about the estimation of the population parameter. So the whole idea of creating a prediction equation is, you there is always a trade off between the bias and the variance of the equation or of the estimation of population parameter. So you don't need too heavy bias and you don't need too heavy variance. You need to balance those two. And when your curve when your equation overfits your sample space, that means you have introduced a lot of variance in your equation. Or when your equation underfits your sample space, that means you have introduced a bias in your equation or in your estimation of population. What you need is a balanced trade-off between bias and variance of the estimation of population parameters. Thanks for tuning in. I made this podcast to talk about intuitions behind data science, and we'll talk about some other idea in the next episode. There will be no math, no equations, just intuitions behind data science. See you soon.